Hello, my name is Alejandro. For the first exam, I'm gonna be working on homework 15.3. For question number one, we have a boat is at anchor outside a harbor. A steady ocean wave makes the boat bob up and down with a period of 6 seconds, an amplitude of 1 millimeter. The wave have a wavelength of 34.5 millimeter. For this wave, what is the frequency? Okay, that's the first thing we have to know, that we are looking for frequency. And let's see what is given to us. We know the period is 6 seconds. Amplitude is 1 millimeter. And wavelength is given to us 34.5. Okay, we need to find the frequency. We should know that there is a relationship between frequency and amplitude, and is given by formula. Frequency is equal 1 over period. We know the period is 6 seconds. The frequency will be 0.1666667 second to the power of -1. That's the same as roughly 0.17 hertz. Okay, that's the answer for frequency. Okay, we have B. What is the wave speed? Wave speed. Uh, okay, the formula for wave speed is speed is equal to frequency times wavelength. We have both frequency, we just got it, which is 0.17 hertz times 34.5 millimeter. We calculate. Is roughly 5 meters per second. 87 meters per second. See, where's the angular frequency? Angular frequency is given by the formula W 2 pi 2 pi over period. We know period. We know it's given to us as it's 6 seconds. Yeah, this is the relationship between them. Is this formula? Two. We calculate 2 times pi. roughly 1.05 radians per second. Okay, that's the angular frequency. What is the wave number? Wave number is given by formula A equal to pi over wavelength. Do we have wavelength? Yes, we do. It's at 34.5 millimeter. 34.5. Pi. Roughly 0.18 radians per second. And that's the answer for the first question. Question number 2. Sound waves in the thin Martian atmosphere travel at 245 meters per second. What is the period of 125 Hertz sound wave in the Martian atmosphere? We are given sound waves in the Martian atmosphere travel at 245 meters per second. That will be the speed. We are given the speed, which is 245 meters per second. We need to find the period. We don't know what it is, but we know the frequency is 125 hertz. There is a relationship between period and frequency. Is given by frequency is equal 1 over T we know the frequency. We know the frequency is 125 hertz. Actually, let's do something better. Let's redistribute frequency. The period is going to be roughly 0.008 meters. I'm sorry, seconds. Okay, F. What is the wavelength of 125 hertz sound wave in the Martian atmospheres? Wavelength of 125, that's the wavelength, is what we need to find. We have a frequency, which is 125. There is a relationship that we can use here. We have the period, and we have the speed. So we can use formula Uh, Speed equal frequency time wavelength. Speed 25 wavelength. We know the speed is given to us and it's 245. 245. See, and the wavelength is roughly 100. Oh no, sorry, 1.96 meters. That's the answer. Okay, for G. What is the frequency of sound wave in the Martian atmosphere that has wavelength 3 meters? Okay, what is the frequency of sound wave in Martian atmosphere that has a wavelength of 3 meters? It's given, the wavelength is given to us. It's 3 meters this time. Frequency is what we need to find. Like before, we know the speed, which is 245 meters per second. So we're gonna use the same formula before. Speed equal frequency by wavelength. Wavelength, is 3 meters. 245. Now the frequency is roughly 81.67 hertz. H. What is the angular frequency of sound wave in a Martian atmosphere that has wavelength 3 meters? Okay, wavelength we know is sorry. Wavelength we know if 3 meters. We need to find the angular frequency. There is a relationship between those two. We know the between angular frequency and frequency. You know the angular frequency is 2 pi frequency. Uh, we know that we know the frequency because we just got it here. 81.67. And we calculate. 51, 113, radians per second. That's the answer for H. Okay, let's do question number 3. You are testing a mountain climbing rope that has a linear mass density of 0.0650 kilograms per meter. The rope is held horizontal and is under the tension of 8 times 10 to the power of 2 Newton. To simulate the stress of supporting a mountain climber's weight, what is the speed of transverse wave on this rope? Okay. We are given the linear mass density, which is 0.0650 kilograms per meter. Tension is also given to us, which is 8.00. And we need to get the speed of transverse waves on this rope. Okay, the formula for the transverse waves this rope we're gonna use is gonna be speed equal root of tension over the linear mass. We just plug in tension. It's gonna be 800. Okay, 800. This will be roughly 107 meters per second. That will be the speed. Okay, J. You oscillate 1F the rope up and down in SHM with frequency 25 Hz and amplitude of 5 mm. What is the wavelength or the resulting waves of this rope? Okay, we need to find the wavelength. We have the frequency, which is 25. Amplitude is also given to us. Okay, let's see if there is any relationship here. Wavelength. We know the speed, meters per second, and there is a relationship here as given by the formula. Speed is frequency times wavelength. Speed is given by meters per second, frequency 25 Hertz times the wavelength. We redistribute 4.44 roughly. Meters. Okay, that's wavelength. Okay, at t equals 0, the MVR oscillating is at its maximum possible displacement and is instantaneously at rest. Write an equation for the displacement as a function of time at the point 2.50 meters from that end. Assume that no wave bounces back from that end. Okay, we need to write the formula. It can be modeled by for displacement. It can be modeled by T equal cosine where amplitude is given to us, right? I believe amplitude is given to us. Amplitude is given to us at 5 meters. Amplitude is given to us is uh, cosine k will be the wave number, and it's given by 2 pi over wavelength. 2 pi over wavelength, which we have because we found it on part J. Let's work with that. It will be roughly 1 point. Okay, the point is given to us. It's gonna be 2.50. Angular frequency, we're gonna be using the same formula that we used before, 2 pi over period. By our period. Okay, no, we're gonna use a different formula. We're gonna use 2 pi times frequency. this should be enough for us to keep working. Frequency is given to us is 25. But and let's complete the formula. The cosine minus 50 by t. 5 cosine times is roughly this. This will be the model. This will be the model of the formula. Okay. Question number 4. The tension in a long string is 25 Newton. You oscillate one end of the string up and down with frequency 45 Hz. When this end is at its maximum upward displacement, the nearest point that is at this maximum negative displacement is 0.400 meters down the street. What is the speed of wave on the string? Okay, let's read one more time. The tension in the long string, tension is given to us. It's gonna be by 24. You oscillate one end of the string up and down with frequency 45 Hz. When this end has a maximum over displacement, the nearest point. What is the speed of wave of one's? What is the speed of wave on the string? Okay, we need to find the speed of waves. That will be given by the form. Okay, and we know that the wavelength is half. We know that the wavelength is half the length between the maximum and the negative point, which is 0 point meters. Now the wavelength then is 0.800 meter. Like I mentioned before, we're gonna use the formula speed equal wavelength times frequency. That's the formula relates all of those. Speed is what we're gonna find. Frequency, we have it, which is 45 Hertz times I don't have a space. Time. And we calculate. 36. Let me double check that. 45. And the speed is going to be given by 36 meters per second. And finally, M. Where's the linear mass density of the string? Okay, we need to find the linear mass density. There is a relationship. We did it before. Well, I believe is related to period. Speed. We are going to move to the other side. Okay. We have a period, each gonna be 25 Newton. We have uh, a velocity, sorry, speed, which is 36 meters per second. Um, times to the power of 2. Final answer will be, let me double check. Point zero, roughly uh, kilograms per meter. And that concludes my exam number 1.